Okay, so today is Sunday, May 16th, and because it's a weekend, so we actually still get we got a hard question for today, but luckily it's only one question, so we will probably be able to like read the solution, learn something, and solve this hard question together. So today's question is number 968 binary tree cameras. So it's although and yeah, it got 15, almost 1600 upvote, only 23 downvote. So this might be a really good question for us to learn. And yeah, so let's do it together and see if uh, I will be able to solve this question or not. So first, let's read the problem together. So binary tree camera. Given a binary tree, we install camera on the nodes of the tree. So each camera at a node can monitor its parent, itself, and its immediate children. So calculate the minimum number of camera needed to monitor all nodes of the tree. Okay. Hmm. So for the first example, this is a very basic tree. So we have one root, and then left child have two child, and then if we install the camera in the middle, we can monitor all of the node, include itself. So the minimum requirement is 1. But for the example 2, yeah, the minimum is 2 because this one can monitor the root, this one can monitor the leaf. So the minimum requirement for this tree is 2. Okay. The number of nodes in the given tree will be in the range of 1 to 1000, and every node has a value. So the node value is not important in this one. The tree structure is more important, I think. Okay, and there's no hint. And here we have our tree node. That's just a regular tree node. Okay. Look like simple, but it's actually a hard question. So because you know that's a hard question, so you probably won't try to like brute force it. So and luckily we know that this is hard. Otherwise, if I would encounter this one in the interview, it looks so simple though. I probably would try to brute force it because for now I don't have any good idea to do this other than simulation. Like for this one, I will probably actually put camera in here and then try it and then realize that I need 3 and then try this one. So oh, that's brute force, right? So how do we do better? To brute force it, it's probably DFS. So DFS plus memo, which is DP, but the problem is first, it's a tree. I know how to DFS. How do I memo? How do I memorize though? And do I need to memorize? Will I call the same thing twice? I don't think so. Because once I put the camera here, I then try to put camera in here. Will I try that again? So after I put, for example, 2, after I put the camera in the first position, and then when I move to the second position, do I need to try both, like put camera here and not put camera in here? Because I think I don't probably need to check both condition, because if I have a camera here, I don't need the camera in here. So I will put it in the next position. And then, okay, so if we do DFS, we can probably count. But there will be a backtrack though. Like, I try it, and then not tried it, and it's a binary tree. So it's 2 to something, right? So it won't work. The time complexity is too high. Okay, give me like 3 more minutes. I'm going to see the solution because this is a hard question. I don't expect myself to know every solution, especially for the hard question. I think if we can read the solution, we can learn something. So, but before giving up and read the solution, I want to see if there's any other way I can do it. I don't need to try brute force. Time complexity too high. How many node? 1,000. Too high. Okay. Dynamic programming. I don't know which to memo. I don't know how to design dynamic programming. If in the beginning I don't even know how many nodes we have, how do I do the dynamic programming? Recursive call. So tree traversal is always recursive call, right? So for how many camera in here? So if it's a DP, how many camera in here is the sum of, not the sum. Okay, I got the idea of DP. So I need to know for my child until that point how many camera is already set. And if the child have the camera, how do I make it a function? How do I return that? Right, because if I know how many camera, so that there will be a DP for, so my DP will probably is an array list because I don't know how many nodes that we have, right? And then for the DP, I need to save how many camera for my child, and then if my child has a camera, so if my child don't have a camera, my both child don't have a camera, then I will need a camera on me, and then the camera count will be my child plus my child plus 1. Okay, and then if I got the both child's camera return, and then I know one of the child have a camera, I don't need it. So the sum will be the camera and camera plus 0. Then I return my minima. But how do I know it's a minima? Because my return value will affect my parent, right? Because it's either my parent need to put a camera or not. It's completely based on if I have a camera or not. Count all even number node depth. Well, that's because I guess you probably see this, right? But the problem is they give you a too simple tree for you to look at. I mean, like I said, it's a binary tree. I have 2 child. As long as one of them have a camera, I don't need a camera. So whether a node have 2 child or 1 child is actually affect the entire structure, right? So it might be that, yeah, because if you look one by one, so if you don't check this one, for example, one, if you don't check this one, right? So if this one don't have a parent, and then the return value of the two child, one of them have camera. You don't even need the camera here, right? But the fact is that this current node actually have a parent. So it's actually better. We got better result that this one, if there is a camera in this one. So that's why I think even node might not work, because if we remove the root and use this as a root, the second level are actually both even, but only one of them need the camera, right? And still depend on what's the tree structure after that parent and then after that child, right? So one might have, so when you have two child and only one of them need a camera, how do you decide which one, right? So if I have a two child and both of them have camera, then that's definitely not the best solution, right? Because I'm wasting, there are two camera cover the same parent node. So when you have two child, you know only one of them need camera, but which one? So that's why I think you probably need dynamic programming. But dynamic programming is something that you always save for current node. You always save the best result, right? But now I don't even know if my best result can be used for my parent though, because my best result is either the two different camera return and then plus me or not plus me. Yeah. But the two different child return value will be different with and without camera. So how do I know which one is better? Yeah, so that's why I think probably even though would not work. Yeah. And partially because of this is a hard question, so that's why I guess it won't be that simple, right? Okay, I'm thinking about DP. I'm just not sure how to make the DP work, how to design this DP, because I don't see a way to break this problem into a smaller problem consistently. Or count all the even number node. If I do it from the end, like every leaf node, but it still won't work. Let me draw something. Yeah. So if I have this and this and this and this, but for this only have, so for this one, even one is this. But if you go from leaf, the even one is this. So this is probably not the best result, right? Also, this is probably the best result because we can use two camera to cover this. So for this tree, the answer is 3, I think. No, you don't even need this one. The answer is 2. Ah. Yeah, the answer is 2 for this tree though. Because you only need what's my pen? You only need this one. You only need this one. How do I get it? You only need this one and this one, right? So the answer for this example is 2. But if you count the even one from back, you will also mark this one. Oh, my pen is not working. How do I? Change the size. Yeah, you will probably mark this one, but you actually don't need this one. Okay, so that's that. How do I remove? How do I erase? God. Control Z, 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 Control Z. Okay. So I already wasted a lot of time. I think this is a DP though. I will probably read the solution to see how this DP is designed. So because the problem is, even though you know it's a DP, you don't know how to break down the current problem into a smaller problem efficiently. So yeah, I'm going to give up and learn this hard question by reading the solution. And I don't feel shame on doing that. Okay, so let's read the solution. But it looks so simple though. Approach 1, dynamic programming. Is there approach 2? Approach 2, greedy. Let me read the first one first. So when you have a greedy, it's probably during the process of doing dynamic programming, you figure that you are not actually choosing a sub problem. You always only choose the best sub problem. That's why you can do greedy. But I don't even know how to define the dynamic programming. Okay, so let's read it together. Let's try to cover every node, start from the top of the tree. Working down. Every node considered must be covered by a camera and the node or some neighbor. Okay, because the camera only care about local state. We can hope to leverage this fact for an efficient solution, especially when deciding a place to cover. We might have to place the camera to cover some subset of this node. Its left child, yes. So if I put the camera in myself or my child, I am covered. But why this DP don't consider my parent? I don't know. Because my parent, if my parent have a camera, I am covered too. Okay, let us solve this some information about how many cameras it takes to cover the subtree at this node. Subtree at this node, which means current node as a root. And then there are accessories 3 state. 3 state. Okay, so we either is a strict subtree. All of the node below this point are covered, but not this node. Oh, okay. But you have to smart enough to find out the 3 state cover all the condition, all the different possibility, right? So the first one is that all my child is covered, but not me. And I don't even care about my parents, so I will probably return this 3 state to my parent, right? And then normal subtree, all the node below, including myself, are covered, but there's no camera here. Placed camera, so all the node below, including this node, are covered, and there is a camera, which may cover nodes above this node, so which may cover my parent. Oh, this is so complicated. Okay, so once we frame this problem this way, the answer falls out. To cover the state 1, the child of the node must be in state 1. So for cover myself, my child will be a normal subtree. Hold on, how? Oh, yeah, that's true. So if so the state 1, if I am state 1, the only possibility that is true is because both my child are covered, but none of them have a camera. So I will be in state 1, like I'm not covered, right? And then to cover a normal subtree without placing a camera here, the children of this node must be in state 1 or 2, and at least one of those children must be in state 2. Because state 2 is actually placed camera. So, like I said, if I'm covered, then one of my child should have camera, right? So one of my child should be in state 2. And because state 1, okay, but not both of my child in state 2, right? Because it will be a waste. It would be a waste if both my child are in state 2, because I don't need two camera to cover myself. To cover the subtree, okay, I'm reading this line. To cover the subtree when placing a camera here, the children can be in any state. Sure. Okay, so we are basically have a DP to cover all three states of each node, right? I think. So we call this and we call our help function. Oh yes, now I understand. So our DP is saving all three states value for every node. Or not every node. It's just myself. Oh, just myself. So this is a size of 3 array containing the value of myself, right? And then because if myself is in state 0, then I can return the answer. So the answer is definitely the root being covered. So it's either the root in state 2 or 3. Whoa. So this DP is actually quite simple, but I just cannot figure it out. I cannot figure it out. I cannot figure out those three states. But it turns out, but it's it's not actually simple. So this is a top-down DP. So you see every help function have a recursive call, have two recursive call actually. So you recursive calling your, so the ending condition is that if current node is null, then I return the cost of state 1 is 0 camera. The cost of state 0 is 0 camera, state 1 is 0 camera. The cost of state 3 is just, I think this it will be equal than like integer max value. I think that's why he used 99999, he or she, because we just want to, when minimize it, we just want it to return 0. That's what I think. Okay, so we first recursively call our children, and then minimum of the left 2. Oh my god. Is the minimum of the 1 and 2. Minimum of the right 1, 2 is minimum of right 1, 2. Okay, so I want to know the minimum of 1, 2 from my left or child, because I consider myself is a normal tree without placing a camera here. So this part is actually doing this part, I think, right? And then now we have D0. D0 is just the left 1 plus right 1. So D0 is the value of here. So if I am not covered, so of course it is both in state 1. And if I am normal tree, I'm covered, but I don't want a camera on me, then it's the minimum of, oh my god, L2 plus minimum of the M12 and L1 minimum left 1, 2. That makes sense because one of them should be in state 2, right? And as long as the left in the state 2, then the right, I actually don't care about you have camera or not. I just need the minimum value of the camera. I don't care do you have a camera or not, right? So it's left have camera and then the minimum number of right, or right have camera and the minimum number from left. So that's my state 1. And my state 2 is to cover subject when placing a camera here. The children can be in any state. So 1 means that I put a camera on me, and then max minima is any state, right? So any state, I already have the minimum of the 1, 2, and then I min again with 0. So this means I put 1 camera in here and I want the minimum value from left. I want the minimum value from the right. And then return my current status. Wow. Okay, the code is short. I'm not gonna able to come up with this idea. No, never. So my question now is, how do people find out that this TP will eventually become a greedy though? How? Let's read the approach to greedy. Instead of trying to cover every node from top down, let's try to cover bottom up. Bottom up. Consider placing a camera with the deepest node first and working our way up the tree. If a node in its child covered and has a parent, then it is strictly better than place the camera at its node's parent. Hold on. If a node has its children covered and has a parent, then it is strictly better to place the camera at this node's parent. That's how we know it's a greedy. Oh my god. Okay. So the thing is, I'm a node. I have 2 children. So if I already know that I don't care about whether of either or one of them have a camera or not. If I know both of my children are covered, I don't need to put a camera on me. I only need a camera on my parent to cover me. It will strictly better because we are coming from the leaf level, right? That's what I think, because the leaf will always have but why? How do you prove this is? I mean, for greedy, you always prove with contradiction, right? So you first know that this is our greedy statement, and then we made a reverse statement, or we negate it, and then said that, okay, let's assume that when my children are already covered, I still put a camera on myself, and I got a better result. And then I use math to prove that it's impossible. Then that's proved by contradiction, right? And let me guess, there's no proof. So how do I know this greedy work? How do I know this greedy work? I mean, intuitively, I think it's probably true. If my children are already covered, why do I put a camera on me? Because it's a waste, right? But how do we prove it though? I mean, if you are going to do a greedy without a proof, you don't know it's actually working. But there's no proof. Anyway, but let's read the code, right? So start from leaf. So how do we get to the leaf? We have a main camera cover, and the answer is 0. So and then we have a hash set. I don't quite understand. Hold on. And then we add a null, and we DFS from root, and then return the answer. Hold on. So the set is a tree node covered. So we memorize what the node are covered, and the answer is also global. Okay, and then we add the null. Why? Okay, so let's see the DFS first. So we have a node. We have a tree node parent. Oh, that's parent. Okay, par is parent. Okay. Okay, that's why we add null, because if I'm root, my parent is null. Oh my god, now I know. Okay, so if node is not null, then if current one is not null, then we DFS our left, our right. Otherwise, not otherwise. And then after we DFS it, so the thing is, after we DFS, the answer already contained the camera count of my children, right? So I know my children is covered by calling the DFS. And now, if my parent is null and I'm not covered, or so this means root and I'm not covered, or I'm not root, or I'm at just regular node, and my left is not covered, or my right is not covered, then I need to put a camera on me. Okay, so let's reread the condition. If I'm root and I'm not covered, I need to put a camera on me because there's no parent can cover me. That makes sense. And if my left is not covered, then I put my camera on me. Oh, yeah. I need a camera if my child is not covered, right? So if any one of my child is not covered, the only way until now, because we are doing backward, right? I already called the DFS on my child. So when we return from the DFS, if one of my child is still not covered, I need to put a camera on me. Otherwise, my child will be left dead in there. There's no camera covered. Okay, so that makes sense. Answer plus because we put a camera on me, so me myself add it to the cover, and then I will add my parent to my cover list because yeah, if I have a camera, then all the 3 nodes are covered. It doesn't look like a. I think it follows the greedy algorithm in here. But if they didn't tell me this is greedy, I wouldn't know this is greedy though. Okay. And our ending condition is the node is null, right? So because our DFS only do things when when we are calling with a non-null value. So actually the DFS ending condition is calling with a null value. Okay, so of course the time complexity is n because every node only traverses once. The space complexity is the height of the given tree because we are trying to call it recursively. No, this edge is actually wrong, right? Because we are having a covered set. The set size is not the height, right? Am I reading it wrong? Because the covered will be probably approximately less than half of the size of the tree, right? But it will not be the height. I think the height is because that we are calling DFS. We are calling recursively, so it is a system stack. So and then the way that you can say that the space complexity is the height is that because you should be guaranteed that the set covered is less than the height, is always less than the height. Can you prove that? I also don't know if you can prove that though. So so this also I read the solution, I know how to do it now. I don't know how to prove it. I don't know how to prove it. I mean, for greedy, I was hoping that anybody can prove it. And top voted 400. Oh, lead 215. Okay. And it's using DFS. And then the second one is DFS. It doesn't mention greedy, but ON is definitely greedy. DFS, greedy DFS. Naive DFS, then that's greedy. So any of them prove that? Any Wow, his is even shorter. I mean, most of the time, I won't be able to understand lead 215's solution though. Okay, so consider a node in a tree. It can be covered by its parent itself, two children, four options. Consider the root of the tree. It can be covered by left, right, and itself, three options. Consider leaf of the tree. It can be covered by itself and parent, two options. If we set a camera on the leaf, the camera can cover the leaf and its parent. If I set a camera in its parent, the camera can cover leaf, parent, and siblings. So we can see that the second plan is always better than the first. So it is trying to prove the greedy. Now we only have one option, setting up camera to all leaves parent. Is this considered a proof of the greedy? Now I understand. Okay. So here is our greedy solution. Okay, I'm glad that I read his solution. Now I understand. So set camera on all leaf parents, then remove all covered node, and then repeat step 1 until all nodes are covered. So explanation: apply recursion on DFS. Return the 0 if it's leaf. Return 1 if it's parent of a leaf, or when camera is on the return 2 if it's covered without a camera on this node. This is a little bit confused for me. So for each node, if it has a children which is a leaf node 0, then it need camera, which is the parent of the leaf. It's covered. Hold on. for each node, if it has a child which is a leaf, then I need a camera. If I have a child that is a leaf, if it is has a child, if it has a child which is a parent of a leaf, then it's covered, so I don't need a camera. If it need a camera, then rest plus plus. If it's covered, we return 2. Otherwise, we return 0. 0 is that we are a leaf. Oh my god. Okay, so I'm glad I read this. So the intuition actually proved that we should do mathematically, not actually, but not actually approve, but it is telling that how we come up with this greedy idea, right? So his code is even shorter. So if it's null, it's a null, it's covered. So we return 2. Wow. I would not thought of that. Okay, so if left, and then still for the greedy, we first call the recursive call it with left and right, and then if left is 0, 0 means leave, and then or right is then we need to put a camera and return 1. Otherwise we return left is 1 or right is 1. I am still confused because those if the parent of a leaf, if it's covered without a camera of the node, so we return 1 on what condition? On okay, I sort of understand, but I am confused. So after we reach like level, because you only care about if there is a leaf or not, right? So I have a leaf, I put the camera on the parent, and then the parent's parent don't need a camera. Then go up another level, we need a camera, right? Okay, so I think this is a little bit confusing. Return 1. So the return 1, not only if it's a parent of the leaf node with a camera on this node. Actually, he return 1 when there is a camera on this node. You know what I mean? Because you don't only like you don't only put a camera on you when you have a leaf as your child. You put a camera whenever your next one returns 0, right? And your next one will return 0 if it's not 1, right? So it's like leave and return 1, and then return 0, return 1, return 0, return 1. So 1 does not always means that you are a parent of a leaf. It actually means that you have a camera on this node. So I think only this part is a little bit confusing and not so correct. Otherwise, the algorithm is quite correct. So let's now pick one to implement. Okay, which one? I think both are hard for me. Although I already know it's greedy, it's hard for me to define. I mean, without knowing this, without reading the solution, it's already hard for me to define these 3 conditions. And for this one, is it easier? This one, for me, it looks like it's a little bit easier though, because I only consider if my child is covered or not, right? So I know that Lee 215's code is so elegant, so beautiful, but if I would try to read the solution and implement myself, this is still too complicated. I can do it now because I just read it. After 1 hour, I will forget what I read, and I will never be able to implement this again without reading his explanation again. So I will probably choose this one though, because this one for me is easier to understand, right? Let's read it again. We have a global answer. We have a set of all the node that is covered. So we initialize the global result to 0, and then we initialize the hash set, and then we add null because my root, as a root, my parent is covered. But I still don't know why, if we do need to do this. Because do we ever check if parent is covered? Yeah. I I one thing, I actually doubt that we need to do this. But maybe I'm wrong. Because if you check in the if statement, we check the parent come from here, right? If the parent is null, and if cover contains current node, and if cover contain my left, if cover contain my right. Oh, but my left or right could be null. Okay, so we add this null actually not for parent, actually not for root parent. We add this null is just for you to conveniently call cover contain left. Otherwise, you need to check left is null or cover contain left. Then you need to check right is null or cover contain right. But by adding a null into the cover set, the code looks shorter. And that's the only reason we need to add the null into the cover set. Oh my god. So it took me read it the second time for me to understand the code. I still but I still think this one is more reasonable for me to implement myself compared to Lee 215's code. I love his explanation so that I understand why greedy works in here. I can't wrap my head around this 3 condition. I will forget. So let's try it. It's almost, we still have 1 hour or more. Let's try to implement from the official given solution, okay? I'm not going to try the dynamic programming at all, because I can't remember this kind of condition for. I cannot even design these 3 conditions myself. That's why I can't design a dynamic programming for this question, because I don't have the ability to come up with this. So let's do the greedy, okay? So just, I forget things. So I would like to implement in here instead of here so that it's easier for me. Okay. So let's try it. Okay, so first, let's move out of the code. Don't come back to the code here until I need it. Okay, we have, let's call it rest. I always call my answer rest, so I don't want to call it answer. Okay, And then we also need a global. If we don't do a global, we probably can pass the set into the recursive call, right? It will cost me more memory, but I don't care. I'm not competing with anybody else with the memory usage, right? So let's not make it a global, shall we? No, not integer, tree node. So we use a set to memorize what's the cover. covered. Did I spell it correctly? I think so. New hash set. Okay, we got a hash set. Now let's call our DFS. DFS. Reconnect. Okay, so I guess I have a glitch on my network. Am I back? Am I back? Okay, I guess I'm back. Sorry, I have a glitch on my network, so yeah. So now I'm back, but I'm not stable. So, oh my god. But okay, so let's quickly do this question. So because I guess now my network is not stable anymore. Okay. So where is my mouse? Where is my mouse? So we have a covered, and then now I already know, but I will make a comment on that. So I will covered covered dot add null, right? And then I will comment that to myself so that I know that this is for not needed to check whether a child is null. Okay, I have so many typo, but anyway, as long as I myself understand whether, how to spell whether. Well, anyway, as long as I understand, I don't know how to spell whether. Okay, so now we add that. So let's recursively call our DFS with the current node, which is root, and my parent, which is null. And again, I don't need to, so I guess that will be in my declaration of my DFS. So return rest. Return. Okay, now let's do our DFS. PRIVATE. Do we return anything? We don't need to return anything, I don't think, right? And then DFS, and then we have a tree node cur, which means current, right? And then we have a tree node parent. I need to spell it out so that I know it's parent, so that I don't need to make a comment on that. Okay, so the ending condition, I always do an ending condition first. So I will always check if cur is null, then I return. I just return. I don't do anything, right? So I do this so that I understand what's the ending condition of the recursive call. And then now we recursive call our left child cur.left, and then let me copy and paste again. Right. And oh my god, my network is not stable, so let's quickly finish it. So after I recursive call, I know uh it's almost like a DP, right? After you call the sub problem, you know that the sub problem are solved. So let's check. So now let's check whether I need to add a camera on myself. So if I am the root, if I am the root, which means that my parent is null, and I am a root, and one of my child is not covered, right? Uh, is that right? Hold on. I suddenly forgot the condition. So the reason why I need a camera is one of my child is not covered. So let's do that first, okay? So if not covered contains cur.left, or not covered contains cur.right. But I remember there is a root. There is a thing that root you need to consider. I sort of remember not remembering what it is. So let's think about it. So if I'm root, oh, if I'm root, then only when both of my child is not covered, only when hmm. Oh, if I am a root. Ah, I still a little bit confused because I don't know if my I only know my child is covered or not. I don't know if my child have a camera on them. Then how do I decide? So if both my child are covered, and then because I don't have a parent, oh, I think root is the same. What's wrong with me? We passed the parent in here. Until myself, do I know if my parent is covered? Okay, sorry, I'm gonna give up and read the solution again. So I am, oh, okay. Although I'm, okay, now I understand. Sorry, let me put it back. I should not look. The reason why checking ourselves when calling DFS on ourselves works, because if my child has a camera, when I recursively call DFS on my child, if my child decides to put a camera on themselves, the children will put me into the covered set. So when it returns, also I am still within my own DFS call, I might already be added into the cover set by my children. That's why. Oh my god. Because I was thinking that I am still in the DFS call for myself. How do I know? Right? How do I check whether am I covered or not? But the reason is my children are good children that they will put their parent into a cover list. good for them. Okay, so no matter I'm rude or not, if one of my child is not covered, I am going to put the camera on me, or I am root, so which means my parent is not null, is null, and covered contains cur. So okay, I want to separate them because I want to make comment so that I remember. Sorry. So this is condition for every node, and this is condition for root. Okay, so to put a camera on me, so this is to check whether to put a camera on me, right? So if this is true, then we put a camera on me. How? So first we res plus plus because we put a camera on me, right? So and then we covered where did I do wrong? Why it's not also auto condensing? Ah, God. Okay. Cover dot add myself, which is cur, and then I will also cover my parent. So the code is here. The cover parent code is here, and that's why we most likely need to pass a parent in here, right? And then I don't care. I will also add my left and my right. Are we done? I think we are done. I think we are done. So I think this is the code that we can try. But I will always have compile error. So method DFS in the class situation cannot be applied for the given types. Oh, shoot. Cur. Do I? Okay, call again. That's bad. It's not returning. Arrow cannot find symbol. Covered. Oh God, because I didn't make it global, so I need to pass that in here too. Let's do it. Let's do it. Let's do it. Set Trino covered. And let's pass the covered into our next call. Ha! It's wrong. So where did I do wrong? Res? Did I make it 0? But it will be 0 without initializing it. Right? So how do I get 2? Res is 0, this is this is this, and I call myself, so if it's null, return, so we call this, so And then if so, let's assume we are leave, right? So if cover not contents left, cover not contents right. So if one of them is not content, then I'm going to add, or if my parent is null, which means I'm root, and then cover not content. Better. Do we have other test case to test? Better. Shall we make test cases? I don't even know how to make test cases though. 0, 0, 0, 0, 0. Okay, so I think it's good for us to do our daily. But to be honest, let me submit it first. Okay, but to be honest, I don't feel like I learned anything. I learned that if I got the same question in the interview, I might remember how I did this. The problem is, for a greedy question, this cannot be applied on other similar question though, because every greedy question have its own way to solve it. So now, although I did finish submitting a hard question, I feel good. I feel I understand something, but I don't know if I learn something so that I can apply to other things though. Yeah, I don't know. And if I check the result, I think everybody's code is similar, right? Oh, everybody's code is better than me. I don't know what to say, but oh my god, I already learned nothing, and then still everybody's code is better than mine. But I like this question though. I like that it's a hard question and the coding in the end is so simple. I don't like it's a greedy question because I need to mathematically prove that the greedy algorithm work. And I don't like that for a greedy question, every question is different. So I learned this, I did this, might not help me solving other greedy questions. So let's just hope that I won't receive any question like this during the interview. And that's it for today. I have bad internet, so I better end our daily streaming right now. So I don't know, but hopefully you learn something or you feel like you enjoy something. So I guess the key that I still learn today is that for a greedy type of question, you need to quickly determine if it's a greedy and discuss with the interviewer to see if the greedy works. And if he or she let you keep coding, then you might be right. So you need to grow an instinct of determining whether or not this is a greedy question. So that's what I learned from today. So hopefully you learn something too. And that's it for today's daily. And I am thinking that tomorrow we will back to having a medium question. So hopefully tomorrow will be a day that I don't need to read the solution first in order to solve the daily question. Okay. Thank you for watching for today's daily. And then I will see you tomorrow. Thank you. Bye bye.